So now we come to the pole in the barn paradox, one of the famous paradoxes coming out of the special theory of relativity. You can see we've already written a number of things on the board here, so we can save a little time as we go along, but we'll take it one step at a time, make sure we understand where we start and where we end up, and in between where we go with it. So here's the situation. Back to Alice and Bob again. We assume Alice has some pole vaulting ability, so she has a long pole that is 10 meters in her frame of reference. Okay, so Alice's pole here, 10 meters in her frame of reference. And she is moving, she's very fast pole vaulter. She's moving at a velocity of 0.6 times the speed of light. That gives us a gamma factor, Lorentz factor of 1.25. And then we have Bob over here. Bob owns a barn. It's Bob's barn. And his barn is 8 meters long. Okay? Not a huge barn, but 8 meters long there. And that's in his frame of reference. Again, Alice's 10-meter long pole is in her frame of reference in terms of how she measures it. When it's stationary with respect to her, she gets out her tape measure. It's 10 meters long. When Bob is stationary in his barn, he gets out his tape measure. And it's 8 meters long for him. They both have accurate tape measures. And Bob also has, the barn has a door in the front and in the back, which we haven't shown here, but you can imagine that. And clocks, 2 clocks synchronized, one at the front door and one at the back door. And now let's just write down some of the key numbers here. In Alice's reference frame, of course, her pole, L sub pole sub Alice, A for Alice, of course, is 10 meters long. But in her reference frame, Bob's barn is Lorentz contracted. So it's a 1 over gamma factor here. And the proper length of the barn is 8 meters. And so we've got 1 over gamma, 1 over 1.25 times 8. 8 divided by 1.25. You get 6.4 meters. So from Alice's perspective, from her frame of reference, she sees Bob's barn as 6.4 meters long and her pole as 10 meters long. Meanwhile, Bob, in his reference frame, he sees his barn, of course, as being 8 meters long. And he's observing Alice's pole as she's coming along here. And again, Lorentz contracted. And so 1 over gamma, the 1.25 factor here, times 10 meters for her pole gives us 8 meters. And so what Bob says to Alice, Alice, hey, why don't you run through the barn here? I'll open the doors. And in fact, do a little test here. Just as you get inside the barn, okay, or not just as you get inside, but as you get all the way inside the barn, so your pole reaches the back door, I will close both doors simultaneously. And clearly there's enough room, if I do it quickly enough, very, very quickly. My barn is 8 meters long. Your pole is 8 meters long. Clearly there's enough room to close both doors simultaneously. You'll fit just nicely. And don't worry, I'll open them again really quickly so you can keep running out there. And of course, in actual fact, you couldn't do that, and poor Alice would splat against the back door probably. But to make the situation a little more realistic, perhaps, we won't have the doors closed. We'll just have Bob take 2 photographs. Okay, so as Alice comes through here, Bob again will see the barn is 8 meters long. Alice's pole as also 8 meters long. And just when Alice's pole reaches the back door here, he'll take a photograph of the front of the pole, and at the same time, according to his perspective here, the back of the pole should be right at the front door, and he'll take a photograph then, simultaneous, and therefore he'll see the front and back of the pole in both photographs, and the 2 clocks will be synchronized. They'll both read the same thing. Alice, meanwhile, is thinking, Bob is crazy here. There's no way my 10-meter long pole is going to fit inside his barn there, because it's not even 8 meters, it's 6.4 meters there. And so she thinks he's crazy. So let's analyze this and see what happens if they'd actually do something like this. And we'll assume that the front of the pole here, as Alice runs through the barn, enters the barn at 0. Okay, so Alice's clock reads 0, Bob's clock reads 0. We can certainly do that. For one space-time point, we can synchronize clocks. We can't assume that other clocks, though, of course, are synchronized in terms of, Alice's Latticer clocks is synchronized to her. Bob's Latticer clocks is synchronized to him. But we can't assume that just because Alice and Bob have synchronized one pair of clocks at a certain space-time point, it means Alice and Bob's clocks, of course, are synchronized in other instances as well. So let's see what happens. Bob's observation is pretty straightforward, assuming we think about just the fact that he's got 8 meters here and sees that Alice is coming toward him at 0.6 c meters per second. And we want to first just figure out how long does it take the pole to reach the back door. So again, the pole enters right at t equals 0 here, traveling along, reach the back door. Well, it has to go 8 meters from here to here as far as Bob is concerned. It's at 0.6 c meters per second. When you do all the math there and get the units right, you come out with 44.4 nanoseconds, billionths of a second there. So that's what Bob reads on clock number 2 here. In other words, the front of the pole reaches the back door in 44.4 nanoseconds. And actually, the rear of the pole, the back of the pole, reaches the front door in that same time because, again, it's 8 meters long. So when the front is here, the back of the pole has to be here as far as Bob is concerned. So both clocks will read 44.4 nanoseconds at that point in time. And so Bob says, hey, no problem at all here. What's the deal? Alice, don't worry about anything. Well, let's look at what Alice observes then, because clearly from her perspective seems, how can Bob close both doors or take both photos and show that my pole, the front of the pole is right there and the back of the pole is right there? There's way, it's way too big here, 10 meters versus 6.4 meters. So let's break down Alice's observation step by step. So remember, from Alice's perspective, it's not she who is running toward the barn. The barn is actually approaching her. It's coming toward her. In her frame of reference, she's stationary. And so she sees, and again, we start at t equals 0, right when her pole gets to the barn here. Really, I should say, the barn gets to her, the front of her pole, and that's at t equals 0. And then the question is, okay, how long does it take the back door to get to where the front of the pole is? Well, from her perspective, 6.4 meters, that's how long the barn is. So 6.4 meters, the barn is coming towards her at 0.6 times the speed of light. Do the simple arithmetic there, you get 35.6 nanoseconds, billionths of a second, to reach the front of the pole. So the rear of the barn takes, from the time the pole just enters the barn, or really the barn just gets to the pole, it takes another 35.6 nanoseconds from the back of the barn to get to the front of the pole. And then you look at that and you say, well, how can that be? Because Bob's clock reads 44.4 nanoseconds. How can Al's be getting 35.6 nanoseconds? Well, we have to remember a couple things here. We've done things like this before, actually. So, this is Alice's clock. If she's observing Bob's clocks, she observes them running slowly, right? Moving clocks run slow. As far as she's concerned, Bob's clocks are approaching her at 0.6 c. They're running slowly. And so we get the 1 over gamma factor. So in actual fact, this doesn't even seem to help, though, because she says, okay, hey, Bob's clocks are ticking off between the time the barn reached the front of the pole and then moved back, so the rear of the barn got to the front of the pole. On my clock, on Alice's clock, 35.6 nanoseconds. But if she's looking at Bob's clocks, they're ticking more slowly compared to her by the 1 over gamma factor. So it's actually 28.4 nanoseconds. It seems like we're going in the wrong direction here. We're trying to get to match 44.4 nanoseconds because, remember, there was a photograph taken right at that instant in time. Just when the pole, the front of the pole, reached the back door, Bob took a photograph. Everything was there, all Alice's clocks, she has clocks on her pole, and 44.4 nanoseconds, and yet Alice is saying Bob only reached 28.4 nanoseconds. Well, one other factor, as you probably have read ahead here, you can see here, I didn't write it down, but you should recognize this, leading clocks lag, right? It's a relativity of simultaneity. Many of these relativistic paradoxes in terms of the special theory of relativity go back to, have at the heart, their foundation, this idea of the concept of relativity of simultaneity, that what is synchronized in one frame of reference is not in another. So remember the formula for that. Again, so Alice is observing Bob's clocks coming toward her. She's looking at 2 of Bob's clocks. They're at the front and the back. Leading clocks lag. This clock number 1, is going to lag clock number 2. Let's focus on clock number 2 for a moment here. At TA equals 0, okay, that was when the barn just reached the front of the pole. Bob's clock number 2, as Alice observed it, she had her Lassa clocks and took another photograph right at that point, would be reading dV over c squared ahead of this clock. Both clocks, both Alice and Bob's clocks, remember, were synchronized at 0 at that point. So it's 0 at this point, and if Alice snuck a photograph of clock number 2 at that instant of time in her frame of reference, she would see clock number 2 for Bob not to be synchronized with this one, but to be running ahead. Remember, leading clocks lag, so this one is running ahead, and it's the dV over c squared factor. One of the reasons we did that calculation a while back, so we could do things like this and actually make it consistent, make it come out. So what is that? Well, remember the d here is the distance between the two clocks in their frame of reference, and the distance is 8 meters in Bob's frame of reference. So we have an 8 for d. V, of course, is 0.6c, the relative velocity between the frames of reference, and c squared on the bottom. Do a little bit of that algebra, and you get 16 nanoseconds. So, look what happens. When the barn reaches the front of Alice's pole, this is at, her clock says 0 nanoseconds, and it takes her as the barn comes and reaches the rear of the barn, reaches the front of the pole. She observes Bob's clocks tick off 28.4 nanoseconds. So in other words, the front clock, if she's watching that one, goes at 0 and ticks off 28.4 nanoseconds when the barn then reaches the front, the rear of the barn reaches the front of the pole. But this clock number 2 is already ahead by 16 nanoseconds. So what we have here is it's running 16 nanoseconds ahead, plus then it ticks off the 28.4 as the barn moves to that point where the rear of the barn reaches the front of the pole. And add those together and what do you get? 16, it was running ahead by 16 nanoseconds. 28.4 nanoseconds ticked off while the rear of the barn moved to where the front of the pole was as far as Alice is observing. And you get 44.4 nanoseconds. So when that photograph actually occurs, yes, both Bob and Alice agree Bob's clock should read 44.4 nanoseconds, but for different reasons. Bob for a fairly straightforward reason, just 8 meters divided by the speed of the pole going through. Alice, a little more complicated calculation because we have to take into account these relativistic effects, but yes, she can agree that it reads 44.4 nanoseconds. She doesn't disagree with the photographic evidence, though she does tell Bob, your clocks are really messed up, Bob. You need to get that fixed. Okay, so that takes care of the back door in terms of 44.4 nanoseconds at that point. But remember, going back here, Alice thinks the barn is 6.4 meters long. Her pole is 10 meters long. That's not a thing. She observes those to be that way. So when the rear of the barn reaches the front of the pole, her pole is still sticking out. And so that's our next question. What we have to do, what about the front door? What's going on with the front door in terms of the photograph that's taken then? Because remember, Bob had 2 photographs taken, one at the front, one at the back, and both of his clocks read 44.4 nanoseconds. We've matched up the back door situation. We understand that. Now we need to look at the front door situation. So let's get a little room here with that. And let's do it over here because we want to leave some of these numbers up here, and these are pretty basic. We've got the 8 meters and all that down here, so we'll remember those at least. Okay, let's draw a little diagram. What's going on at this point? Again, from Alice's perspective now, from Bob's perspective, straightforward. Just two synchronized photographs, front and back, 44.4 nanoseconds. Pole is right there. Boom, we're done. Okay. Now, though, let's look at. So let me just emphasize this. Okay, so this is the key figure, the 44.4 nanoseconds there, and remember how Alice got there. First, she saw her clock ticked off 35.6 nanoseconds, but then that actually means Bob's clocks tick off 28.4 nanoseconds because of time dilation as she is observing Bob's clocks. And then we've got the leading clock's lag factor from the clock number 1 versus clock number 2, and that's 16 nanoseconds. And then you put those together, the 16 plus 28.4, and we get the 44.4 nanoseconds, which Bob also saw on his clock and which was in the photograph. Okay, so what about the front door? Let's draw a diagram here. So actually, we'll just put it on here because we got the barn already here. So at this point now, here's what Alice sees, something like this. Okay, where the barn has been rushing towards her, and we're just at the point where the rear of the barn reaches the front of the pole. Did the analysis there, got the 44.4 seconds. But remember, she sees the barn not as 8, but 6.4 meters, because it's length contracted. So for her, she's got 6.4 meters of the pole inside the barn at this instant, and another 3.6 outside, because the pole is 10 meters for her. Okay? So what's going on? Well, again, remember, we need to have a situation such that when this end gets to there, when really from Alice's perspective, when the front door gets to the rear of her pole, this clock needs to read 44.4, because that's the photograph Bob took. Well, again, remember the leading clock's lag effect. At this instant in time, okay, when this photograph is taken, we know that clock is reading 44.4 nanoseconds. In Alice's frame of reference, this clock is ahead of this one, and by a factor of 16 nanoseconds. So in fact, from Alice's perspective, when this reads 44.4, the front one here is going to read 44.4 minus 16, which we've already calculated, actually is 28.4. So 28.4 nanoseconds. Okay? So now imagine Alice in very, very slow motion here. She's watching the barn go by, and she's watching Bob's clocks tick off. And so the barn is going to move now from, let's maybe do this in a little green here. So the barn, front of the barn is still moving with respect to her, and it's going to move to that point right there, and that's when the photograph will be taken, Bob's photograph showing his clock. And so let's analyze then how long that takes with respect to Alice's frame of reference. Okay? Well, again, this is just V here, 0.6C. So she has to watch this, so it's 28.4 nanoseconds, 16 nanoseconds to go on Bob's clocks here until it gets to 44.4. So the question is, how long does it take the front of the barn here to get to the end of the pole? Does it take that extra 16 nanoseconds? On Bob's clocks, yes, but what about Alice's perspective? Once again, we have to remember time dilation. From Alice's perspective, she's seeing Bob's clocks tick slowly. And we used it over here. And in this case, we know that Bob's clocks are going to tick 16 nanoseconds from here to here. Because again, we know the photograph was taken at this point, and at that point, clock number 1 reads 44.4. And right now, it reads 28.4 from Alice's perspective. Difference is 16 nanoseconds. So Alice is going to see Bob's clock tick off 16 nanoseconds while it goes, the barn goes from there to there. But it's not 16 nanoseconds for Alice. Bob's clocks are running slowly, so for Alice, it's more time. In fact, it's gamma times 16 nanoseconds equals 20 nanoseconds. Okay? During the time, Bob's clocks tick off 16 nanoseconds while the front of the barn is traveling toward the end of the pole as Alice is observing it. Bob's clocks are going to tick off 16 nanoseconds because, again, we know we're at 28.4 here. We know the photograph is taken at 44.4 nanoseconds according to this clock here. So we've got the 16 nanosecond difference. During that 16 nanoseconds on Bob's clocks, Alice's clocks tick off 20 nanoseconds. Okay, so from Alice's perspective, she's waiting 20 more nanoseconds for the front of the barn to get to the rear of the pole. And how long, what distance does the barn cover during that period? Well, we just do 20 nanoseconds. That's how long we have on Alice's clocks. And a speed 0.6c. That's how fast the barn is traveling along here from her perspective. If you do the math here, 20 nanoseconds times 0.6 c, you get 3.6 meters. In other words, the exact distance the front of the barn needs to travel to get to that point, according to Alice's clocks. So somewhat incredibly, it might seem, everything checks out. Everything is consistent, except, of course, Alice and Bob disagree on whether things are synchronized or not. Bob is saying, hey, my clocks are synchronized. Okay, clearly, and with length contraction of your pole, clearly your pole fit in my barn. Okay, because I have photographic evidence of it. The front of the pole was at the rear door at 44.4 nanoseconds, and the front door was at the rear of the pole and fit just inside, also at 44 nanoseconds. What is there to debate here? Meanwhile, Alice is saying, well, you know, somehow I made it through here, but clearly your clocks are off, and clearly at this instant in time when your rear clock was reading 44.4 nanoseconds and we took the photograph, or you took the photograph there, I agree with that. Yes, it is 44.4, but the pole was still sticking out by 3.6 meters, and it's only because your clocks are so unsynchronized that once the barn actually got to this end that it registered 44.4 nanoseconds. So yes, I agree with the photographic evidence there, but I disagree that the pole actually could fit inside the barn. It's because if we were actually closing doors, you'd have to close the door quickly here and then open it again so that the pole could get out. But again, it goes back to the relativity of simultaneity, which in turn goes back to the fundamental postulate of Einstein that the speed of light is constant in all reference frames. Once we had that and the principle of relativity, then we started building these principles on top of that and got to things like the relativity of simultaneity, like time dilation, like the length contraction, and then Lorentz transformation after that. And now we're working out some of the consequences in examples like this. Again, we don't see this typically in real life because even though technically it does occur in real life, but the velocities involved are so small that the time differences are so small, and length contraction is so small that we just don't observe it unless you're using very precise physical experiments.